Hello, Johnny Vandefort here, Lorain County Community College's MEMS, Microelectronics Manufacturing Program, and Merit, Manufacturing, Electronics, and Rework Institute for Training. I had some time, so I thought I'd record a video on something that is to me fun yet challenging to be able to do. Everyone has had at some point an idea to bring into reality, a concept that they want to design and show somebody the results that they can prove that what they design is functional. And a lot of times when I'm working with students within my program or trainees that were within my program, they have ideas related to a microelectronic product, a printed circuit board, typically of some sort with it. And so, what I would like to show with you right now is a series of very summarized steps. There are a lot of things that go into the design of electronic product. And I'd like to bring some basic ones to a more hobbyist level, how to get something started from more or less from scratch, almost as if you didn't even know yeah, a great deal amount about it. And sort of what we use within our degree and training programs to be able to teach students how to do this for the first time. So without further ado is designing a microelectronic product 101. And this is just saying that this is first step. So this would be for somebody who has been curious, like what does it take to build an electronic product? Do I need a lot of fancy equipment to be able to do it? What are the typical steps involved with how this is going to be, and so forth. So let's get started. In reality, designing a microelectronic product actually takes a great number of steps to go all the way from a design to a fully like flushed out, being made in a factory product. But there are three very key steps, three milestones, if you will, in terms of being able to do this. And the three large milestones. First one involves a project management, how to manage a project. Second one is a concept and design. This is actually drawing it up. And the third major one is the actual manufacturing involved with the actual product. So first you plan what you want to do, then you design it up, simulate it, etc., and then you manufacture it. Each one of these has some summarized steps involved with them as well. Let's go into some details about sort of what those are. And actually, the very first one is an important one. Underneath project management is to define the specifications, or as many people refer to it, is the spec. Now, the spec is ultimately what constitutes a passing product, right? What are the boundaries that take place for designing the spec? In terms of some things to take into account would be its function. What does the electronic product actually do? What is the uh, uh, thing in which the product needs to be able to work with it in terms of how do it work is what it is. Another one that I wrote down to this in terms of, I wrote quite a few of them on here, would be its size. Be another thing to consider. How big is it? Is it meant to be a portable device that is meant to run on batteries, or is it something that plugs into a wall or a USB port of some sort and has some sort of a external energy device in terms of what it is? I'm going to call the next one on here the history. Has anything else like this already been built? A lot of times we designers kind of look at, has the wheel already been invented? Has somebody actually made some progress towards what it is that you're doing? Or has someone already invented what it is that you're doing and you're looking to make it a little bit more novel, a little bit more you in terms of just being the designer? the history is an important one with that. Its cost is an important one to consider. How much money do you have to spend, or do you want to be able to put into the product by which that you are working on? Let's also talk about another one that's very important to lots of people is the reliability. How long is the product meant to be working for? How long do we expect its lifetime to be? How long do we expect to be making the product? Uh, so on and so forth with that. Regards to mainly, how long do we expect this to work for? And then another one that I wrote down on here is repairability, the ability to repair something. Is it meant to be discarded, or is it meant to come back to us to where we can finagle with a few things? There are many others. One actually that just came to my head that's a very, very important one would be the safety. Is the product safe? Are we marketing it to the right people? Are we bringing it to using materials that are safe materials of which to build it? So things along those lines there. There are many more. I could write, and many people have written books on just this step alone, but it is important to at least define it for what you want to do. Don't get trapped in this step of defining the specs and in project management in general. There are lots of people who have an idea and they get trapped with just thinking of the idea because they are afraid or unsure of how to go on to the next steps of actually designing it up. Um, so don't stay within these areas here, right? The next one is an important one. This is define what makes the project done or complete. What is the last, where's the finish line? This is so important, and it has to deal with what I talked about in the last time. Like, what does it mean to make the project able to be complete, like done, and at that point we consider this to be a victory at that point. So having the project have some sort of a defining what it is to be complete for this is very, very important for us. A letter C is a timeline. Goals are important to be able to set. We should set them with reason, and at the same exact time, be aware that we have an overall project timeline. How much do we divide up into each one of these kind of areas for that? So having a timeline is important, but also having flexibility around the budgeted timeline is with an understanding that in some cases we may need to extend time or hopefully get things done early and we have extra time to spare, but at least have a goal set in mind for what to be able to do for that. And then a last one out of this is define the team members. Many designers will frequently not work by themselves in a variety of areas. One could not necessarily be an expert in all areas related to microelectronics. There's usually a multidisciplinary team, electrical people who are familiar with electronic function, mechanical people who are familiar with the artwork and the layout and how the overall board is to be designed, the machine and fabrication people who actually build the circuit board up, the manufacturers who do the circuit board in terms of soldering all the components together, the testing people, and then even beyond that, simple concepts such as like if you're making a mobile device, does it feel good when you're holding it in your hand? Are there sharp edges that are annoying to deal with? Is there a potential power source on it that is in the wrong orientation or confusing to be able to have a battery put into it? By wrong orientation is, will it fall out of the device if it's being used? Is there a switch that turns it on and off that is difficult to access? Things along those lines there. Defining the team members, and there should be a team. The designer should consult with somebody along the way to be able to determine whether or not if something has been made successfully for that. So 4 areas of project management, of which we will go through as an example. I've got a circuit board that I would like to make and windows that would like to be updated. Thank you very much. I'm going to close that over to the side right there. Glad my face was covering that. Ugh. All right, the second area of circuit board design. Oh, good. I've got this again. Another one. Do I need to pick a time for this here? Oh, boy. On there starts with something very important, the schematic. The schematic is a series of symbols that are connected to each other to definitely show electronic connection and fairly frequently show how a show some location of where the parts tend to be as well. So it's definitely how they're connected, but also where their location relative to each other might be. The second area that's important is the bill of materials, or sometimes abbreviated BOM, BOM. The bill of materials is the source information. Where do we buy it from? How much does it cost? Is it available? All 3 of those are of concern in a lot of ways. The third area, I think a lot of people would just commonly refer to this as PCB design, but I usually like to refer to this with the word of layout. This is very much an art piece in a lot of mechanical ways, but also a lot of artistic ways. This is all related to art with an understanding of what it is. And so I'd like to kind of keep that in mind. I'll be calling it layout the entire time for this. And throughout all 3 of these, I'm going to call it feedback, right? Or second eyes, or A, 2A through 2C. The second pair of eyes, right? Don't just design it by yourself. Someone may have some insight that you wouldn't even expect to show up. Even if it's an expert, someone who is being called in to see how something was technically made, versus someone who is just random, just be like, does this make sense? One of the guys that I used to work with, who was an engineering manager, would frequently call in someone like the shipping guy or the janitor, and just to come in and be like, hey, is what we're talking about making any sense? One time in particular, I think the shipping guy said something related to like the salt that's on the road and how that might affect how the thing might work. It turns out he was right. And none of us brainiacs in the room could think about that. It took the FedEx guy to be able to do that. So it was a really cool thing to be able to see. Lastly, in the overall process is we need to manufacture this. Manufacturing first starts with a first functional prototype. Prototype is the very first version that has ever been built. This is often expensive, ugly. It's never built the way that you think it's going to be, but often involves a lot of trial and error to prove that the design is actually functional. It generally comes with quite a bit of testing, and troubleshooting, right? These A and 3A and 3B really kind of go together in a lot of ways. We're not always sure that our design is actually going to work. We're not always sure that the what we have designed has been designed correctly. Even if we have 10 pair of eyes on it from step 2D, uh, there may still be a problem that we all missed. This happens to my students every once in a while, where I, the student, and one additional student peer, we all have eyes on a project and still something escapes us. It happens from time to time. But we need to be able to find it and fix it as fast as possible, right? Sometimes what that involves is if there is something that has to be done on the testing and troubleshooting side, I'm going to put on here rev where needed, and that's revision, right? Revision. Change the revision, update it. Update what was happening before until it was working, and make sure that the revisions are documented and controlled, right? This is, for instance, like, say, for instance, we make the first functional prototype and, oh, egads, something's wrong with it in a bad way. So we go back in and we say, all right, let's fix the thing that's wrong. We found what it is. We fixed it. Let's identify the new product with something on it that is visually intuitive for us to be able to see what that is. While at the meantime, additionally, recording somewhere in notes with the documentation what was fixed and where for that. So it's very, very, very important for this right here. C would be to build. Oops. Oh, I did click the new page on there. Sorry. This is build more than one, right? Make sure that beyond the prototype, you go to additional boards being built. There should be additional boards to prove that it's not just one and done that just made the whole thing. Although in some instances, maybe the project is like that in very advanced cases. But for a hobbyist level, yeah, maybe there's want to be proof within the pudding that something is actually functional, that the concept has been done. But definitely build something that is presentable. Present product, right? Present what you have built to somebody. Show somebody that it works and it works well for that one there. And in fact, once it's done with that, the last step that's in here is report and standard operating procedure. Oh boy, procedure, which I'm going to call SOP, right? The report is to report on what was done. How was it done? A reflection of the whole thing. But very importantly, as you are taking notes along the way, create an operating procedure of how to build it. It may be years down the line where you actually want to build another one, and you may not remember all the steps that you were doing right at that moment. So you want to build an operating procedure along the way that shows that how someone else of your skill level could build that particular product. Can't stress how important that is, because very frequently I'll design something, I'll build it, I'll build a bunch of them, and then 3 years later, I'll try to remember back to what it was that I built. And it's a good thing I often write an SOP on how that's done, right? Those are the main steps. Take a moment, write these guys down, think about them in terms of what they are and how they are. And let's think about them in particular as we are going to recreate them ourselves for a new project for this. So I'm going to skip to new page for this here. And actually what I'll do is I'm going to insert a page number on bottom of my page. I do this if I ever have multiple documents in terms of, or a document that has multiple pages in it. So this is page 2 of, and then I'm going to insert a quick parts where I'm going to put the page number is where that is. Oh, num pages, I think. Yeah, there it is. Number of pages. That way that's being tracked with each one of those. So, project management. I think for this one, I'm going to call this one, just as an example with this here, Lily Blink is what I'm going to call this. Just a name that I'm going to call in terms of what this is. Let's talk about what I want my project to ultimately be. And I'll record kind of examples of this here, we'll say in blue in terms of what we're going to be doing. So let's talk about the spec. We're going to design, and well, I thought I changed the font, but lo and behold, it's not changed at all. Design and build 2 circuit boards that use a 555 timer to blink. We're going to call it here 10 LEDs is what it's all going to be. That's going to be what our circuit is ultimately going to do. We're going to say that the circuit board has a switch and can run on a 3-volt battery, like one of those little watch batteries, like a watch battery. We'll say that that's kind of a part of that. We'll say that the circuit is, how big should we make this circuit board here? We'll say it's going to be PCB will be 25 millimeters by 50 millimeters and will not have sharp edges for that. So we'll say that that's kind of a part of that here. Additional parts to this will say that the circuit board cannot cost more than, let's put a price on here of, say, $10, including the board. So we'll say that all the parts that we're using just to make one board will not cost more than $10 for it. We'll also say that the battery can be easily replaced by sliding out. No screws to hold it in. Something that's a simple one. And then also that the LEDs are casually visible by an observer more than 10 feet away. Something along those lines. And not just the LEDs, the movement of the blinking of the LEDs are from that part away. So I won't get into much about the repairability, the reliability. I will, safety-wise, I will get into something. Circuit is built from RoHS solder, right? RoHS means restriction of hazardous substances. Solder, frequently from a hobbyist perspective, is lead-based, or the element lead. In the periodic table, it is capital P, lowercase b. This is a carcinogenic material that is overall easier to make prototypes with, but however, is a toxic material, and I want to avoid some contact with it in particular for this project. Most of the time with my students, I tell them to first design something in lead just to get something functional. It's easier to start building something with lead, but in the end product, when I'm making this finally, once I've figured out that the design is competent, I'm going to use lead-free solder. So lead-free solder is lead-free, which is what I would like this to be. Design what makes this project done or complete, right? So what's going to make this project done and complete is going to be having 2 RoHS assembled boards, one that I give away to someone, right? Something along those lines there. Going back actually up to the top, something that I always tell my students to put down, it would not be proper if I didn't do this myself, PCB must have artwork unique to designer on the PCB. I will design something that's on there in terms of where that is. A sample timeline of what I think I can reasonably do this in. Now, I have done this many, many times in the past. So what I'm going to put down is, typically speaking, I actually run very similar projects with my students, often at a often within a let's say an academic environment of 16 weeks of a semester. And so I'm familiar with kind of the general setup for how this goes. I'm going to put down here 4 weeks to design schematic, 4 weeks to design layout, 1 week to, or we're going to call this 2 weeks to buy parts and build, or buy parts and write documents, These would be like, for instance, the building documents. Usually I have a piece of paper or a notebook or something handy where I can read what I need to do. And then 6 weeks to manufacture and test uh, test PCB. That's what I would like to be able to have with this. Now, for team members, I do need to be able to include some team members for this. I would like to have some input from someone. So input on PCB design. I would like to have somebody related to do this. So I'm just going to leave this as kind of a blank spot for this right here. I'm going to leave another one kind of sitting right here. Switch back to blue for some weird reason. There we go here. I would like to have input from testers, right? So I'd like to have someone to be able to kind of test this out in terms of what this is. So eventually I'll want to have like two inputs and two inputs from here. And then we'll kind of leave it sort of as that. So there is my project management slide in terms of what I'd like to do. This timeline right here, and I might speed through that a little bit in terms of going through the overall process for that. But at the same exact time, this is what we usually give to my students as well. One of the things I'd like to talk a little bit about, though, is so I'm an electrical engineer. I understand concepts in electronics, and I've done this quite a few times before. So I'd like to talk about the circuit board from a block diagram perspective. Many people think that, like, oh, I have to begin at the wiring schematic and the schematic for how all the parts are connected. When in reality, that's actually not really what you want to do. In reality, we want to kind of put this as a series of steps and fill in the circuit boards if we know kind of a little bit about what's here. So we're going to start here in, I'm going to call this kind of in a brown color right here. And I'm going to say for this part in particular, this is going to be where I put in the 3-volt battery. The entire circuit board will be powered by a 3-volt battery. And so this is going to be a modular type of device. This is going to be a device that powers every part of the circuit board. And I'm going to put this kind of at the top part of it here. This is to say that everything is powered by a 3-volt battery. And actually, in particular, what I'm going to also put here next is that the 3-volt battery is going to next be fed into a circuit device that I'm familiar with, and that is something I can talk about here in terms of what this is. We're going to put next on here a regulator. Not good enough just to have a battery. Usually you need some form of a circuit board or a circuit of some sort that's actually able to regulate the flow of electricity in a variety of conditions. And I am familiar with several types of devices that can do exactly that. These would be chip devices that have some other little components that are attached to it, but I would like everything that I've got on my circuit board here is going to utilize potentially just that. Now, the next thing I'm going to put down right here is an interesting little device. And I'm going to kind of change the shape of this ever so slightly. This isn't part of my specifications, but I actually just kind of thought about it right now as something that would be fun to do, fun to add in for this, as they are not so expensive a device to be able to get, but we shall see. I'm going to put on here a thermistor, right? A thermistor is an electronic sensor that changes its electronic value with temperature. And I think there's a way that we can add some thermistors to our circuit board that might make this a little bit more fun and functional towards making the lights, for instance, blink faster in the circuit board or slower potentially with a couple of the applied heat or something associated with that. So we'll see if we can get away with something like that, if there's something there. I need a circuit next that is going to be able to provide a blink of some sort. So I'm going to put on this one right here. We're going to put on this part right here is blinking circuit. And my thermistor is in particular going to feed that circuit. It's going to provide information from the environment into the blinking circuit to be able to change how that particular part of it works with it. And then finally, I'm going to have one last circuit that's here that is my LED circuit, my light emitting diode. This is my light emitting diodes. The LEDs are going to be the things that blink with my circuit that overall show that the circuit is able to function in a particular way for this. So, and power from my regulator will be getting supplied into each and every one of these guys. So power is just universally being applied to all three of these here. Likewise, the 3-volt battery, I'm also going to put 3-volt battery and switch. So there's going to be a switch up at the top that's going to control this turning on and off for how that works for that. So this is the start. This is the start of how we potentially build something here that will be a functional product. So that's overall how we're going to kind of define a little bit about how this is. Next, we're going to walk through the concept and design and ultimately showcase how that is done. So we'll see you around next for part 2 of how this is done, where we will go into the concept and design. We'll see you later. Bye-bye.